So
Okay, so okay, so Clovis will tell you about a very exciting part of the stellar dynamics, because we are really getting close now to what brings us here, namely the stellar dynamics of extreme mass ratio sources.
okay, thank you. So I continue the talks of earlier this morning by Cole Miller and Mark Freitag on the astrophysics of these extreme mass ratio in-spiral sources. Yeah. So to give an overview, if you need any, I'll give some motivation for why it is interesting to study these EMRI sources. I guess most of you don't need that kind of motivation because you're motivated already by coming here. And then I'll shortly review some relevant stellar dynamics and stellar content in the close environment of massive black holes. And then I'll discuss a number of these mechanisms which make these, which lead to these extreme mass ratio in-spiral sources. And I'll divide them into two classes. First, what I'll call the pure in-spiral problem. So this is really the idea. You have just Newtonian or almost Newtonian point particles. So there's no hydrodynamics or anything. And all point particles are single stars. So I don't consider binaries here. And the question is, how often does a star spiral in all the way to a black hole to become a LISA source? And the reason why I discuss this problem is, first, that there is an astrophysical or an observational motivation, being that this may well be one of the most important contributors to the total number of EMRIs that LISA will observe. And second, it's a relatively simple problem. Somewhat simpler than all the other channels which produce EMRIs. And when I say relatively simple, the word relatively is crucial here, because it's still a very complicated process with a lot of different dynamical aspects that, and consequently a lot of uncertainties. So I'll say something about the in-spiral dynamics. It turns out that this gives rise to some critical distance scale from the black hole. And from this we can learn something about mass segregation, which Mark talked a little about this morning, about resonant relaxation, and we can learn something about the eccentricity distribution of stars that are observed will be observed by LISA. And as the second part, so this will be the main part of the talk, and as the second part I'll discuss some alternative routes to produce EMRIs. And well, I will devote less time to this, but that is not to say that the total event rate will be produced by this pure in-spiral problem. It's just that this other problem is somewhat simpler, and it's interesting to use it as a reference point. So alternative routes include formation of EMRIs in accretion disks. There was some discussion about this morning as well. Binary disruptions and possibly remnants of ultra-luminous X-ray sources. So why are EMRIs important? Well, just some examples. They give some detailed tests for general relativity, and so that's from a theoretical, really physical point of view. From an astrophysical point of view, it's interesting because we can learn something about the stellar contact very near massive black holes and the stellar dynamics very near massive black holes in a region where we have no electromagnetic information. And we learn something about the massive black holes themselves, what their mass distribution is, and what their spin distribution may be, so, and which gives in turn some information about the merger history. We can learn something, if this idea of forming EMRIs in accretion disks, we can learn something about that in an indirect way. We know that stellar black holes exist, and we know that massive black holes exist, but these intermediate mass black holes that everybody talks about, we have only circumstantial evidence, and there are several ways in which EMRIs can give evidence for these intermediate mass black holes. Namely because of these EMRIs. And EMRIs can be two things. An EMRI is an intermediate mass black hole spiraling into a massive black hole. But an EMRI is also a stellar black hole spiraling into an intermediate mass black hole. That would also be in the intermediate mass range. So we have some opportunities to learn, to get direct evidence of these black holes. And finally, this more theoretical point, perhaps massive black holes don't exist, but they're in fact boson stars or some other crazy theoretical thing. Now, Cole Miller mentioned that we have not much information about massive black holes in the range which is interesting for LISA, and that is of course true. On the other hand, we have such a massive black hole in our own galaxy. So we're lucky enough that the kind of black hole that we're interested in is just in the center of our own galaxy, and we have comparatively very good observational data on this. So this is a picture, infrared image of the galactic center. You see there's a very high density of stars. If you analyze this, you find that the density distribution of stars diverges as a power law towards the center. So there's a lot of stars very near the black hole. The size of this image is roughly a parsec or so. This, as Mark explained, leads to a very short relaxation time, which is good because it means stars can change their orbits in the course of time within the age of the galaxy. A star that is initially not on an in-spiral orbit may be changed by encounters with other stars and come on an in-spiral orbit and become an EMRI in this way. And to put some scale, so the black hole roughly dominates the dynamics within a distance of a parsec or so. So that's where the mass in stars is much less than the mass of the black hole. Okay, so this system also immediately gives us the best evidence, I think, for the existence of a black hole. These are observations from the last 15 or so years where stars have been followed really on the plane of the sky. And so our own galactic center is close enough to actually follow these stars and do astrometry on them. And you see that these stars all orbit this point here. And from the orbit, you can first solve the mass of this object and also the density. And this leads to the almost inescapable conclusion that this is indeed a massive black hole. And so we have this really nails down the case for a massive black hole, and people have to start thinking about really crazy things like boson stars and other concepts that are very unusual to come up with alternatives. And another thing I may mention is that this thing here is by some considered to be a candidate of an intermediate mass black hole. So I don't know, everybody may have his own opinion on this, but at least some people claim that this thing here is an intermediate mass black hole. So there is some circumstantial evidence for the existence of that as well. But this subject of the galactic center will be discussed in more detail by Tal Alexander's talk, and I think also by Melvin Davis' talk, so I'll skip that over here. Yeah? It's an old movie, I know. That was an extrapolation, yeah. Well, there are some data on it. Those are, like, the crosses are data for that star is S2. Yeah, that's right. That's right. Okay, so then to turn to the main part of this talk. So this is this pure in-spiral problem. This problem we want to solve here is, what is the rate at which detectable EMRIs form in a system of single point particles near a massive black hole? So no hydrodynamics and no binary stars. And that's just to give a reference point to discuss a lot of the different relevant dynamics and to find finally the rate at which this happens. So the idea is this: in a schematic picture, you have all these stars here very close to a massive black hole at a very high density, and as Mark said, in a typical moment, if you look at this system, there is no star so close to the black hole that it emits gravitational waves or that it's relevant for LISA in any sense. But then, because this relaxation time is short, stars can change their orbits. So a star, let's say this star, was scattered somehow to an orbit where it spirals in. So where it gets, at this point, to a periapse, where it emits some non-negligible amount of gravitational waves. And then two things happen. First, these gravitational waves may be in the LISA band. This is typically not very interesting, because at one single encounter with the massive black hole, even if you emit some amount of gravitational waves that are in the bottom of this sensitivity curve, we won't be able to observe them because the signal-to-noise ratio is not high enough. But another thing that happens is that the energy that goes into these gravitational waves, even if you don't observe them, is taken out of the orbit. So the next orbit will be a little bit smaller, and the next orbit will be yet smaller, etc. So if in this simple picture where we just consider this star and the massive black hole, the star starts to spiral in and gets closer and closer to the massive black hole. However, a complication is, of course, caused by all the other stars, because these stars, which change the orbit of the first star to put it on an orbit where it starts to spiral in, will continue to interact with this star that spirals in. And it can change the periods of this star. So after a few orbits, the periods of this star may grow again, and then in-spiral stops. Or it may shrink, and the star may get lost to the black hole. So that's just a very picturesque way. One remark on this is I said that these bursts of gravitational waves are unobservable because the signal-to-noise ratio is too low. There is one example, one exception to this, which is our own galactic center. If a star comes within a distance of a few Schwarzschild radii of the galactic black hole, which we know exists, then this would be, in fact, be observable. Question is whether the event rate for this is high enough or not. Okay, so let's consider then in a more in this diagram how a typical star spirals in. So in this figure you see, which is by the way made by Tal, you see here the angular momenta of the star on a log scale, and here the energy. So the black hole in angular momentum space would be on the left side of this picture, right? So a small angular momentum means that you're at periods close to the black hole. And there is this red region, which has been schematically drawn as a square, as a rectangle here, where a star that has a very small angular momentum will immediately cross, for example, the Schwarzschild radius, or to be more precise, the last stable orbit, and be lost. So stars in this red region cannot exist. And in energy space, the black hole is here on the top of the picture, so very high energies means very close to the black hole. I use negative energy. I put a minus sign of the usual convention of energy. So the black hole is here. So here again there is a region where stars cannot exist, just because that's a prediction of general relativity, basically. So and here there's a region where there are very high energies, and that means that the period of the star is very small. So the orbital frequency of the star is very high, and that's what's relevant for LISA. So here I'm close to the black hole. There's a lot of gravitational waves. And when a star passes through this region, while it's here, it emits gravitational waves that are actually observable by LISA, because the whole orbit of the star is in the LISA frequency band, and the signal adds up and gets high enough to overcome the noise. So let us then follow some typical star, or some which starts out here at some high angular momentum and low energy. So this star is completely, at this point, completely uninteresting for LISA. However, then it starts to scatter with other field stars, and goes to the left, and goes to the right, and left to the right again. At some point, it will get a very small angular momentum, and in other words, a very small periods, and it interacts with the black hole. These are these bursts of gravitational waves that are not yet observable if the black hole is far away. So the star spirals in a little bit, then it gets scattered away again by stars, because this is an ongoing process. So it goes away again, maybe goes back again, and when it goes back again, it starts to spiral in again. And in this way, at some point, the orbit gets smaller and smaller, so scattering becomes less important. Star spirals in, and in this region, it becomes observable by LISA. So this would be a very nice thing for LISA to have in this example that I just gave. However, another thing can also happen. If we consider a star which is further out, then it has some very high angular momentum, is scattered quite wildly because the orbital period is larger, so the amount of scattering per orbit is larger. And it scatters back and forth, again, just like the other star, loses some gravitational waves, but because the steps in angular momentum space per orbit are much larger, even if it loses a little bit of gravitational waves, it has a high probability of scattering into the loss cone. So from this picture, it's clear that stars that start very close, it's a probability process, of course, but stars that start very close to the black hole to begin with have a good chance to spiral in and lose energy gradually and become observable EMRIs. And stars that are very far away from the black hole have a very small chance to become EMRIs, because even if they have a few orbits at which they emit gravitational waves, they are very unlikely to spiral in all the way to this region. And this means that there is some critical energy which can, or the critical distance, if you wish, which divides these two regimes. So stars that have higher energies or smaller semi-major axis than this critical scale here will spiral in and become EMRIs, observable EMRIs. And stars that are further out or at larger semi-major axis, smaller energies, will scatter in before becoming observable. Okay, so this is a very, well, this idea I give here is in words. So to quantify this, we did Monte Carlo simulations, which were, this idea was, I didn't acknowledge it here, but it was first done by Hills and Bender, this kind of simulations, where we start with a lot of stars at some given semi-major axis, let them at every orbital period, let them scatter in energy in angular momentum space, and drain some energy because of their interaction with the black hole, and see whether in the end stars spiral in or whether they cross the last stable orbit and will never be observable. So if these two lines are not so important, but if you focus on these lines, it's not easy to read. So this is semi-major axis, and this is the fraction of stars out of all stars that lead to observable gravitational waves. Then, just like I said before, very close to the black hole, there is a very high probability that this will happen. At some critical distance, it drops very rapidly. These curves are for different stellar types, and the number here is a few hundredths of a parsec. It drops very rapidly, and here the probability goes very rapidly to 0. So there is this critical distance scale, and to me that's maybe the most important result that I'll show here, which in a way is a bit disappointing. The most important result I quote here is not the event rate of EMRIs is such and such, which is probably what many of you would like to hear. The uncertainties are way too high to make that into the most important result. The most important result here is really a theoretical thing, and that is the distance scale. And I think this is a robust thing. We tried it for many different systems, and it always turns out to be of the order of a hundredth of a parsec or so. So the relevance of this scale is that all stars that, and I still consider single stars, all stars that are inside this scale have a high probability of spiraling in, all compact remnants, of spiraling in and becoming observable sources. Whereas all stars that are further out here have a very low probability. So if somebody tells me that he has some very nice process which does something to the relaxation at this distance, it probably is not going to change the in-spiral rate very much. Because these stars, even if I drive stars much faster to the loss cone, for example, or whatever I do here, these stars have a very low a priori probability of spiraling in. And nothing that's happening here is going to make a very big change, as far as I can see. Okay, a second thing is that we can, from this, find the in-spiral rate. Because the time scale for a typical star in this close to the black hole for the angular momentum to change by a large amount, or change by an amount of the circular angular momentum, is roughly given by the relaxation time. So it takes about 1 relaxation time to make that journey that I showed on the previous slide from a large angular momentum to a small angular momentum. So the event rate is then simply given by the number of stars at some certain semi-major axis times this probability function. So I have to convolve it basically with this probability that it spirals in successfully, divided by the relaxation time, because that's the time it takes to get to the loss cone. And then, well, there is this fraction of stars which should actually be inside the integral. So that's the fraction of some given stellar type. And there is this logarithmic factor, which I will not go into here, but that's just a small effect. So from this, we can just give the event rate. And a nice thing that I should maybe also mention here is that if I can consider different relaxation processes, and the relaxation time can, for example, depend on the distance scale from the black hole. But if I just look at if I would just the relaxation time, the normal two-body relaxation time, is roughly for a single power law at least, roughly independent of the distance from the black hole. It has some dependence, but let's forget about it for a second. So let's say that it's independent. If I would let's say that I use artificially multiply this relaxation time. So I consider much larger or much smaller relaxation times. Let us see how the event rate depends on that. Well, on the one hand, let's say we consider a shorter relaxation time. On the one hand, this will become smaller, this relaxation time, and therefore the rate will become higher, it seems. On the other hand, this critical distance scale here has a dependence on the relaxation time. And of course, the smaller my relaxation time is, the closer I have to be to the black hole in order to spiral in successfully. So these two effects compete with each other. And it turns out that in conclusion that the total event rate is not very sensitive to the relaxation time if I just multiply it by some factor, because these competing effects cancel out. Okay, so before I give some number, at least let us add some realism to this picture. Because I said point particles, well, that also includes a spectrum of masses, of course, because point particles can have different masses. Now, Mark has explained already that if you look at different masses of stars, then the more massive stars are likely to be a little bit closer to the black hole, and the less massive stars are going to be a bit further out from the black hole as compared to what would be the case in a single mass population. So in the example I show here, we considered 4 stellar types. These are main sequence stars. What's this? These are the white dwarfs, neutron stars, and stellar black holes. This here is the distance from the massive black hole. So this is 2 parsec here, which is roughly the radius of influence. So the numbers here, this is not the case for Mark simulation, but in our case, we fixed them. So these are assumptions here, these ratios. And on the axis here is the density of stars. So you see that the stellar black holes have a much steeper profile than the other stars. And in fact, if you look at this critical distance scale, which pops up again at roughly hundredth of a parsec, then the stellar black holes, their density, their number density, not their mass density, their number density is comparable to that of the white dwarfs even. So that, in a sense, is a very good, and this also leads to a much smaller or some profile in the relaxation time, which goes. This is just a 2-body relaxation time, which goes down. So this is actually very good news for LISA, because stellar black holes are going to be the dominant source of not the dominant source only, but also the dominant. Their rate is dominant as compared to white dwarfs and neutron stars. So in this picture, you see the rate, the cumulative rate, is a function of distance. These are the stellar black holes, and their rate is of the order of a few hundred per giga-year per galaxy. So that's not a detection rate, of course. That's the rate per galaxy at which these things spiral in. So it's nice that the stellar black holes, for LISA, it's nice that the stellar black holes are the dominant species because they have a higher mass. So, and the signal that these inspiring objects give goes with the mass of the object that spirals in. So not only is their inspiral rate per galactic nucleus higher, but their signal is also larger. So these two effects add up. Yeah. Okay, then there is this resonant relaxation. Mark promised that I will say something about it, so I indeed will. And that is a completely different relaxation mechanism than 2-body relaxation. 2-body relaxation, as Mark has explained in considerable length, is when 2 stars encounter each other, change their orbital elements a little bit, and then completely forget about each other. So if they will meet again, then the assumption is here that whatever their new encounter will be like, they don't remember anything about their previous encounter. And that is probably usually very well justified because of this precession. So even without thinking about how this how relaxation changes the orbit, the orientation of an orbit will change anyway, even without relaxation, just because of the orbit precesses. That has nothing to do with the graininess of the potential. However, as we well know, for a Keplerian orbit, that's not the case. The orbit just stays where it is. It's fixed in space for a purely Keplerian orbit. So any orbit will just look exactly the same as the previous orbit, not only in terms of the angular momentum and energy, but also the orientation of the orbit in the space, in the sky. Now, there is no such thing as a purely Keplerian orbit. There are also always some things that cause precession. And near a massive black hole, we have to worry about two kinds of precession. One is mass precession, by which I mean that the black hole is not the only component in mass. There is an extended stellar cusp, even at 100th of a parsec, for example, and certainly at larger distances. There are some stars. Even if the black hole dominates the mass, there are some stars. There is some precession. Not as much as you would have in a globular cluster, but there is a little bit of precession. If you come very close to the black hole, then general relativity becomes important. And so general relativity is going to precess the orbit and make it move in the sky, the orientation. Now, if we consider for a second that the case when there is no precession, we consider these two orbits here. So you have two orbits around the black hole. One has this orientation, and one has a somewhat other orientation. And every orbit is going to be the same as the previous orbit for many orbital timescales. Then I can think of the encounter not as an encounter between two point particles, so one star encountering another star, but I can think of this as the mass of the stars being smeared out over this orbit. And they form sort of a mass wire. And I can think of this interaction as the interaction between two of these wires, because every orbit looks exactly the same as the previous one. So these wires are going to torque each other, and this changes the orbit very effectively. And it is only limited by the precession mechanism, whatever precession mechanism is responsible. So in this so, for example, for if not GR, not general relativity, but the extended stellar cluster is responsible, then the relaxation timescale is the order of the mass ratio times the orbital period. So that's this curve here. This is for two different masses, if you wish. So the relaxation time, the resonant relaxation time goes down very rapidly, and this is the normal relaxation time. So that's the two-body relaxation time. So that's larger by, well, 2 orders of magnitude or so than the resonant relaxation time. And here it goes up again because of general relativity. This is all averaged over all angular momenta, these curves. So the nice thing to see here is that they roughly minimize, or certainly they're much smaller than the two-body relaxation time, exactly where this, close to this important length scale. So just where at the length scale which dominates the inspiral rate. So this led to the idea that this may well do something with the inspiral rate, and in fact it does. We did some some calculations to show that indeed it probably increases the extreme mass ratio inspiral rate by a factor up to 10 or so. Now, I don't have time to go into all the details of this, but some remarks. It is very important to include general relativity in here. So if somebody is going to do an embodied simulation, for example, of to calculate the EMRI rate, then it will, prediction is that it will make a lot of difference whether you include general relativity or not. So in fact, general relativity is quite important here. And this statement of 10 depends on some assumptions, and a strange thing which may, I can suggest this question to you, is that I said before that that all these event rates don't depend really on the relaxation time. So why does it make a difference here? It does, but it's not not completely trivial. Why? And finally, we in this Monte Carlo method, we knew what the eccentricity was at every point, so we could plot histograms of the eccentricity of the stars at some given period. So here we choose to do that at 3 hours, which is roughly where the stars enter the Lisa band. We could have chosen some other time scale. So this is the eccentricity of all inspiring stars at the point where their orbital period is smaller than 3 hours. So this is for a massive black hole, and you see that the eccentricities are indeed quite high. They get up to 0.7 or even 0.8 or so, which is as high as they can get. Larger than that is not possible because there is well, I said that the period is 3 hours, so the semi-major axis is fixed, and they can come only so close to the massive black hole without being accreted. And so they have they're skewed towards high eccentricities. In order to find these eccentricities, it is very important to include general relativity again. If you calculate the eccentricity of a star using Newtonian relations or general relativistic relations between eccentricity and energy and angular momentum, etc., you get different results, and it is important to include here general relativity. And this is for an intermediate mass black hole, and here the eccentricities are enormous. It's like 0.998 or so. So that's in fact so hard that at periods the frequency at periods is so incredibly high that it is too high for LISA, and this may be bad news in the sense that LISA may not observe it because most of the energy is emitted at too high frequency. Well, I'll go over this quickly, but these are some issues that should be addressed, and in fact most of them have been addressed. So we have mass segregation, resonant relaxation. Some simulations have, or well, I think only Marx have done both energy and angular momentum, whereas we did some hybrid thing, well, going back and forth between angular momentum and energy, not doing it self-consistently. It's important to include general relativity. It's important to have a high resolution of inspires, so really to follow the star for a long way until it spirals in, and not to be too easy in just assuming that it spirals in. To include stellar dynamics beyond the radius of influence. I said we just fixed the numbers there and made some boundary assumption here. You can include, as Mark does, dynamics also beyond the radius of influence. That may be important. Although you should, of course, worry that at some point you have to make an assumption about the initial conditions, whether you do it at the radius of influence or at some point where the relaxation time exceeds the age of the galaxy. At some point you're going to make some assumption. That's maybe an important point to remember. To use realistic stellar populations, which may depend on what kind of galaxy you're looking at. These are all tricky things because we know, for example, that the initial mass function in our own galaxy in the galactic center is probably different than in other places in the galaxy. So I don't know how to do this properly, but it certainly will influence the results. And then there are deviations from spherical symmetry. I think nobody has done that, and systems that are non-relaxed, or that are just after some major merger or something like that. We're talking about high redshift, so mergers may be important. Anyway, the point is that some of these things have not been addressed, but many of these things have been addressed by different authors. None of them have all be addressed by the same author, which, and that would at least be a goal that is probably achievable. And then the second part of the talk is alternative routes to EMRIs. So that's what is the rate at which detectable EMRIs form by any other mechanisms than the other one. And there are, people have been thinking about a few of these. There may be more out there that people haven't thought of course. And it seems quite promising. It's not clear at all that these event rates are lower. So one thing is, for example, there are, if an accretion disk forms close to a massive black hole, there may be star formation in the accretion disk. And in fact, our own galactic center shows some signatures of that this has happened. You see rings of, or disks of, or at least one disk of stars in the galactic center, of young stars. So there has been, well, people argue, and are probably right to do so, that there has been an accretion disk around the galactic black hole in which stars formed. If that would happen in other galactic nuclei, and in some cases they would be dragged inwards by the gas, which maybe has not happened in our galactic nucleus, I don't know, then these can become LISA sources, of course, at low eccentricities. And a similar thing would be probably the case for if stars could indeed be captured by disks. A second idea is that, and this does not include any hydrodynamics, is that a large fraction of stars reside in binaries. Now, if a binary star is on a very large distance from the black hole, way beyond this critical length scale has no relevance here. That is only relevant for this pure inspiral problem. Let us consider some binary very far away from the black hole on a radial orbit. It interacts with the black hole. One star remains there, and the other one is kicked out as a hypervelocity star. Such stars have been observed in our galaxy. So part of this story at least seems to happen. If the companion of that hypervelocity star is a compact remnant, it remains close to the massive black hole. and so close that it will spiral in. And again, as Cole Miller said, I think, this morning, this will be on a low eccentricity orbit. And in this case, it is nice that all kind of other mechanisms that, in my opinion, could not help us for the pure in-spiral problem, here they can play a role. So triaxiality can play a role here. It drives binaries faster to the loss cone and leads to a higher disruption rate. Another thing is massive perturbers, such as giant molecular clouds or stellar clusters. These are observed to exist in our own galaxy. And as shown by Peretz et al., this dominates the relaxation rate at distances of a few parsec. So there, the orbits of stars change not because of star-star interactions, but because of star-cloud interactions, for example. So this also, so here you can think of all kind of alternative mechanisms which change the orbits of the angular momenta of stars and drive them more efficiently to the loss cone, thus increasing the rate. And the third idea is we see these ultraluminous X-ray sources. One possibility is that the main sequence star is filling its Roche lobe next to an intermediate mass black hole. And if that is indeed the case, then after the main sequence star leaves the main sequence and becomes a neutron star or more nicely a stellar black hole, then it will spiral in also to the intermediate mass black hole. In this case, on a zero eccentricity orbit. So that could in fact be observable, because you don't have the problem I mentioned earlier with these very high eccentricity stars that emit most of their gravitational waves at too high frequencies. Now, a nice thing that is in common to all these three mechanisms is that they all have zero eccentricity, they all lead to zero low eccentricity sources. So they give really a different signature to for LISA, because LISA is sensitive, of course, to the eccentricities, than do these other mechanisms. And to allow some speculation, this could lead to a bimodal distribution of eccentricities, where this peak here, so let's say that LISA, we measure all these eccentricities at some orbital period, then this peak here would come for all these indirect mechanisms, or the non-pure or whatever mechanisms to make EMRIs, and these ones from the direct captures. And the way I drew this schematically and certainly optimistically is that this peak is higher than this peak, but that does not need to be the case. This peak can be much higher than that peak. I don't think we know which mechanism wins today. So to conclude, well, to give a number anyway in the end, I think that the event rates of these pure in-spirals at least will be of the order of 100 per giga-year. But I also hope that I've convinced you that this is really a hard number to estimate. We have to think of resonant relaxation, mass segregation, initial conditions, well, and many other things that I've mentioned. And they should all be done simultaneously. And then we should hope that we have really thought of everything and that there are not things out there that we have not considered. So this number certainly contains a lot of uncertainty. On the other hand, you may say that once we measure these sources, then maybe this gives a lot of information about galactic nuclei that we don't have today, to give it some optimistic twist. This seems more robust, I would say, that stellar mass black holes dominate because they really segregate towards the center. And the center is where, so the central 100th of a parsec or so, which is where the sources come from. I spoke about this distance scale. So this is, so anything that, for this pure in-spiral problem, anything that happens within this distance scale is potentially important, not necessarily, but potentially. Anything that happens at distances much larger than this is probably not going to make much of a difference, except for being the boundary conditions of what happens within here. Direct capture sources are eccentric, and the others are, at least the ones people have thought of so far, tend to be of low eccentricity. Thank you very much.
Any question? Yeah, Pete?
I didn't quite understand what you said about the intermediate mass black hole getting high enough frequency so that you might not be able to observe them. Is this getting to higher frequency because it's the high harmonics of the orbital frequency?
Well, it gets on a very high eccentricity orbit, the star, even at a period of an hour or so. So most of the energy is emitted at the frequencies relevant at the periods. So, yeah, yeah.
And it seems to me that in getting to that point, it may spend enough time in using the electricity, so we would still detect the event that might be able to see the last stage.
Well, I haven't worked this out in detail, so it could be. But my feeling is, since all the time most of the energy will be emitted at these very high harmonics, and only a very short time there will be emission at the lower harmonics. It's my feeling that it doesn't work. But
I would just think if the capture factor of 5 or so large a distance as carry out, then the frequencies might be such that you should be able to see them. It has sort of stronger signals, maybe one would still be able to detect the pattern.
a stronger signal than what?
Than tenfold.
No. When I said, oh, sorry. No, when I said when I talked about these high eccentricities, I meant when a stellar black hole goes into an intermediate mass black hole, not when an intermediate. Yeah. Okay.
I'll bite on your resonant relaxation question, but in two parts. One, why does it make the factor different from other mechanisms? So, secondly, just to clarify, that effector spans over the entire lifetime of several billion years of the system, or is it basically lots early and possibly competing with it?
I'll start with the second part of your question, which is it's over the whole lifetime. So what we did is we solved the Fokker-Planck equations in energy space with some sync term accounting for the fact that stars go lost in angular momentum space because of resonant relaxation. So, so stars are accreted to the black hole all the time, and the question is indeed, can energy, just normal two-body energy relaxation, replenish those stars? I think that's what you're asking about. And the answer is that for the so this resonant relaxation was discovered by Rauch in a paper by Rauch and Tremaine. They tried to estimate the efficiency. We've also tried to do that with very small scale embodied relaxation. If what they got and we got is correct, and the efficiency is as high as they claim that it is, or as low as they claim that it is, then the answer is that yes, stars can be replenished by two-body relaxation, and in the so the number I quoted here was a steady state number. However, I would say that there is still enough uncertainty in the details of this resonant relaxation that that maybe the efficiencies are depending on some things that we're not aware of now and are in fact higher. And well, that's fine, unless they are much higher than we think. If they're higher than an order of magnitude, more than larger by an order of magnitude than what we used, then a crisis can occur, which is that you very rapidly get rid of all the stars very close to the black hole, and two-body scattering is not sufficiently efficient to replenish them. And that would be really bad, because then the rate just basically drops to zero of this pure inspiral problem, because all stars are lost. And to the first part of your question, the reason is that, well, sort of a miracle happens. So if a star scatters in angular momentum space, normally a higher efficiency means that stars get faster to the lost cone, but also cross the lost cone faster. And I said before that these things cancel. However, for resonant relaxation, the relaxation time depends on the eccentricity or on the angular momentum of the lost cone because of general relativity, among other things, but mainly because of general relativity. So a star that is very far away from the lost cone just scatters very fast and gets very rapidly to a few times the size of the lost cone. At that point, general relativity slows it down, and the star starts to move slowly. If it goes away, that's fine. Then it starts to move fast again, gets close to the lost cone again, and there it slows down. So instead of this star just flying through angular momentum space and crossing the lost cone before anything can happen, it flies through angular momentum space and then nicely breaks before the lost cone and slowly spirals in. So this is a nice, sometimes things can spiral in a nice way in astrophysics and physics. GR causes precession, and the precession. It's not redshift. No, no. I hope I. No, no, no. Just to clarify, the way I define the relaxation time in both cases, so both for resonant relaxation and for normal relaxation, is the time it takes for an orbit to change its angular momentum by an amount of the local circular angular momentum. So both for resonant relaxation and for two-body relaxation. Well, I'm sorry, I didn't understand your question, so I cannot answer it, but it doesn't mean that I agree with that last statement. Maybe you can. I certainly believe that resonant relaxation works and that these timescales are correct. Yes. That's on a much larger time scale than the precession. So that's.
That's what you said, right? That the small perturbation to the object uses.
Oh, but the time scale.
Actually change transmit the object in alpha, so that this wire picture does not be applied.
I don't think that's the case. Anything that perturbs these wires will limit resonant relaxation. So we have to look for the mechanism which perturbs it most efficiently, and I think that's precession, not two-body relaxation. So in other words, no, you still have precession because there's an extended cluster of stars.
I thought also that both the last domain and Z conducted the small end, there is another thing in the part of the right, where definitely the normal relaxation time is extremely short, right? And nevertheless, it's very easy to show that resonant relaxation is good. You can follow the time of this and the order from angular momentum. It's true that it is changing linearly with time, not with the and so the basic equations are correct. Just so of course, then the scale needs to be very large. That
We had a scattering background. We did with scattering start. But it's basically just a matter of evaluating the time scales, right? So something is going to limit resonant relaxation, whatever it is, whether it's two-body scattering or precession or whatever. So the thing that changes it at the most efficiently should be considered as the one that limits it. And I think that this is mass precession and not two-body scattering. Well, for a 10 to the 8th solar mass black hole, you won't see anything anyway. You mean the detection rate as opposed to the event rate? Yeah. Well, my impression, I think it's of the order of hundreds of events, but probably I should not be the one answering that question, but somebody who knows better than me to translate event rates to detection rate, because a lot of data analysis issues get in there. So.
One problem about black holes is normally that the number of black holes in the range can be detected at any time. Not a black hole with a mass lower than 0.7 is unknown by a factor of 100 in 10. There's another aspect that I should mention, that we don't know also about the population of black holes. We think we know that a stellar black hole exists. We don't know the number of stellar black holes, depending on stellar formation history, metallicity, and so on. That's another very strong uncertainty in all these things. And even when we have a method to compute the stellar dynamics perfectly, we still need to know what is the stellar population, and what is the history of stellar formation and complexity of stellar accumulation is a big question mark. All these rates are...
I agree.
I don't want to make a conclusion at the end of the Okay, if there is no more question, I think we can thank all the speakers of today again.